So the title of my talk comes from a sort of famous scene in Through the Looking Glass, where Humpty Dumpty is playing some teasing word games with Alice, and Alice gets a little frustrated and said, the question is, how can we have words mean so many things? And Humpty Dumpty says, the real question is, which is to be master? And he's trying to get at the idea of, like, are we the masters of our language, or is our language the master of us? And you can ask some similar questions about large language models, and so I'm going to try to do that today. So this is like a picture I drew of a inferencing in a large language model. We just saw a great keynote talk that dove way deep into what's going on there. This is a much more granular picture, where on the left we have some context, and the context is used to predict like the next word. I don't know how many people, show of hands, sort of have this mental model of inferencing. Some people, okay. Anyway, this was my mental model for the most part, and I think it's a pretty useful way to think about LLMs. However, if you take a sentence, again, the quick brown fox, and run it through a LLM tokenizer, this was taken from a IBM Granite model, you can see that things actually look quite a bit different. So what on earth is going on here? Firstly, we see a lot of these funny G's with a dot on top of them, and those are actually representing preceding white space in a token. And a lot of tokens in the vocabulary of a tokenizer have this. You can see the word the has both a version with the space and without the space. I'll talk more about that. Furthermore, not all words actually exist atomically in the vocabulary. Like the word fox here has no token for itself. It has to be assembled from like an F and an OX. So a consequence of this is the word fox has no direct embedding in the embedding space. We can look at what happens when we tokenize code, very common application. You see here there's also a special funny character for new lines, a C with a dot on top of it. If you look at the indentation, the actual indentation spaces exist as their own token. And some of them are actually quite large, like the one at the bottom. So there are some definite non-word things that exist inside of a tokenizer's vocabulary. And this is, of course, useful, especially if you're running something. This is actually a Granite code variant, so it's optimized for coding. So this, obviously, indentation matters here. We can look at what happens with application-specific queries. Like suppose we had an insurance application. We can see that the word insurance actually has no dedicated token. And so, we might ask, like, does that matter for our application performance or not? You can see also, of course, proper names don't get their own tokenization either. So having seen this, let's take a step back and look at what tokenizers are actually doing. All tokenizers have what's called a vocabulary, and it's really a vocabulary of n-grams, not actual words, that are used to build up larger constructs. And so here's a simple one where I define maybe a little 4-character alphabet and a few n-grams that I can build things with. And if you have this kind of list, you can declare a tokenizer directly with that list like you see at the bottom. In real life, it is much more common to train these things from corpora of real data. And so here's a function I wrote. All the code you're going to see, there's a link to at the end at the very last slide. So here's like a little section where I'm actually producing a trainer for the tokenizer and then presenting it with some data, and like it figures out the tokens that it wants to use that way. So most tokenizers tend to favor trying to use larger tokens over smaller. This first example here is just all single characters, and so that's the tokens that it actually uses. The second example, it's actually able to use some of these larger n-gram tokens like the AA token and the AAB token. And that's typical behavior you're going to find when you try to tokenize stuff. Tokenizers will always fall back onto their base alphabet to try to encode stuff. Like, so here at the bottom is a word that it simply can't construct with anything except a bunch of individual letters. And again, that's pretty typically how these things are designed. It's important because you, at the end of the day, need to represent proper names, programming identifiers, specialized terms. So there is essentially no way you could ever produce a vocabulary large enough to cover all possible things that humans actually type in the world. Tokenizers are often characterized with a measure called fertility, and really it's a very simple thing. You can see here the definition at the bottom. You take the length of a bunch of text just simply in characters and then tokenize it, and the fertility is the ratio of the number of tokens to the raw number of characters. So smaller values are typically better. We can compare tokenizers. So like if I created a tokenizer that just had individual alphabet, it produces no compression at all. It's just the same number of tokens as actual input characters. The vocabulary I used earlier is sort of in the middle. It compresses a little bit, but not tons. And if I produced a vocabulary that was all the possible bigrams, then I basically can cut the size in half. So you can see that these fertility measures are really just compression ratios. One of my teammates pointed out that tokenizers really can always be repurposed theoretically as compression algorithms. Well, that's not really their main purpose for LLMs. So what are some tokenizer algorithms? A very common one is called Byte pair encoding, BPE. Variants of this are used in most of the common LLMs out there right now. The way these things trained is you typically seed them again with just like the individual letters of your alphabet. They split the training text into words, which is a loaded term I'm going to talk about in a second. And it looks at new tokens, candidate new tokens, by saying, okay, if I have an n-gram that I see that is common in my text and I can build it out of two smaller tokens that I already have, I will merge them into a larger token and add this onto my list. And I just keep doing this until some maximum size that the user sets is reached. So when it comes time to actually do the tokenizing, again, we split it into words and break the word into individual characters and then remerge according to the set of tokenized little tokens there. So it starts small and then merges until it runs out of tokens to use, and that's how it gets to its largest token. So I talk about words. The thing that actually defines what we mean by words for an LLM is called a pre-tokenizer, and its purpose, again, is just to take a text and break it down into some of these atomic elements that we can then further split into tokens. So here we find the pre-tokenizer of the model I mentioned earlier, and you can see that here, Fox has not yet been broken down, and so that's, again, the function of the tokenizer itself. You can pull all of these things predefined. If you look at like all the predefined tokenizers from Hugging Face, this is the list. I'm not going to talk about all the different things that they do, but you should know they're there. A couple that are worth noting is the pre-tokenizer base class, so you can write your own, and then sequence, which is just you can take any set of existing tokenizers and run them in a sequence. Tokenizers, as I mentioned earlier, sort of have this concept of the token starts a new word, so it's like basically preceding white space. I think most of the tokenizers you see use some scheme like this. However, there are ones where they do the reverse, and the space represents like the end of the token. And there are even schemes I've seen where they use a special character to represent the, not starting a word, as you see here. So what are some other algorithms? Another kind of common tokenizer is called WordPiece. It works very much like BPE, with the exception of when it's trying to figure out like which tokens it's going to use, it will basically say, okay, if I have 2 tokens that are already in my list, and most of the time they're actually together, then I'm going to pick that as the next token to add. You can see here the one difference is it doesn't really look at absolute frequency, it's more like relative frequency. Another one is the unigram tokenizer. This is a little bit different. The first 2 kind of like work from the bottom up, from smaller to larger. This one is top down. It starts with a large vocabulary and then figures out how to remove tokens from that iteratively. And the way it does that is it will take its current list, tokenize, try a bunch of different tokenizations, and the words that cause the least change to that output are the ones it's going to say are least important, and it will remove those from its list. And then when it does the tokenizing, it again breaks things down into unigram characters, but then tests every possible tokenization using its list. So this is a little bit more expensive both to train and to apply. The advantage is that you're probably also a little more assured of getting the absolute most efficient possible compression from your tokenization. I've been talking a lot about like textual alphabets. Tokenizers all have special tokens that are representing like metadata that's usable by the actual language model. So one is unknown. If text is coming in that wasn't in its alphabet, it can't tokenize, and so it just maps to unknown. It has stuff optimized for code, like Jupyter notebooks, GitHub issues, starting and ending of reasoning for reasoning models, and just other kinds of textual context. So how do these things work inside an LLM? This is the structure of the model, in this case, the Granite model that I pulled up. And you can look here, the actual tokenizing really is living at the beginning and the end. So you're mapping tokens into an embedding space, and then you're doing all the fancy stuff we know and love, all of the attention heads and the internal architectures. And at the end, it has to take that and then translate it back into like the next token for our inference looping. And so one thing that's important to realize is that the entire LLM is trained assuming like the particular set of tokens. And so you can't just change this without breaking the LLM. If you want to experiment with these things, you've got to go all the way back to pre-training and run the whole, pre-training again. As we know, this can go anywhere from like, days to, if you're GPT-5, months and millions of dollars. So it's hard. It's actually hard to experiment with these things. Let's take if you convert that structure into a big O sketch. We computer scientists love our big O. Again, you have like this sort of tallish vector-like objects at the beginning, mapping tokens to embeddings, and you have inside all the attention stuff, which I'm sort of ignoring for my purposes. And at the output, you also have embeddings. So you have these dimensions, V, which is the size of your vocabulary, and D, which is just your embedding dimension. And I'm oversimplifying a bunch of stuff here, but this is kind of the picture. So again, in this model that I used, V is about 20 times the size of the embedding dimension. And so if I drew that same diagram to scale, it looks like this. And you can see that they're really quite tall, and inside just little square, smallish guys. And if you increase the size of your vocabulary, this effect gets more and more pronounced. And in fact, you can imagine as you grew your vocabulary larger, it's like the stuff inside becomes almost like dimensionless points. And the big point is here that the vocabulary size starts to dominate both the memory and the computation of what's going on inside the model. So you say, so we don't actually need all that vocabulary. What if I made a real small vocabulary just of like my individual characters? No, everybody's small. So you could do that, but there's a cost. And again, as mentioned, it's hard to actually experiment with these things. So I used a surrogate of hidden Markov models. I just actually trained tokenizers and then trained HMMs on that. And you can see here, if I use a small vocabulary and try to generate, it's just a bunch of junk. It's not even words. Whereas if I use a larger vocabulary, it's still nonsense, but it starts to become more recognizable as text that people might type. And so what you're basically saying is it's your tokenizer and a larger vocabulary that gives you language modeling fidelity. And although I was using HMMs as surrogates, it's not completely crazy. It turns out that LLMs are actually provably Markov models, and the asterisk is under certain conditions. However, the conditions are really basically how we do inference for most LLMs. So it's just a much, much larger state space than a typical traditional HMM. So anyway, cost versus fidelity implies this trade-off space, as I mentioned. This is a very abstract diagram, and so my y-axis is just sort of some measure of overall grooviness, and I claim that grooviness is measured in Lebowski's. On the x-axis is vocabulary size. So again, as we mentioned, if I try to make my vocabulary too small, I get low modeling fidelity. If I make it too big, I just incur a lot of cost. And so you might imagine it's somewhere in between is the region where we'd like to live, a region of grooviness. And it turns out that somebody took this idea already and produced a truly glorious paper that shows exactly where this trade-off lives. And there's an optimal vocabulary size that trades these things off. And the paper link is at the bottom. I'll be publishing this deck so people can look at it. And if they further show that most of the popular models that people publish are really not perfectly optimal. You can see they're kind of like all the central line there is like the optimality region, and most of the models are pretty far off it. And I don't think this is like truly killing model performance, but it suggests that we might be leaving some performance on the table. So at the end of it all, how does tokenization matter? And when I think about that question, again, I'm mostly thinking in terms of application, application sensibilities. Again, if I'm writing an insurance application, does it matter if like all the tokens that matter to me are in my token list or not? And people have, of course, studied this question. Is it important to tokenize at all? That's what this paper was looking at. And the answer is definitely yes. If you, again, just give it simple unigram tokens, your alphabet, the model can't actually learn its theoretical maximum. You see a gap here, which I circled. It just can't get there from here. But if you give it a richer token set, which is on the right, the models actually can basically reach the optimal performance. So it does matter to have tokens. Again, that's just a more rigorous and scientific study that duplicates what I did here with the hidden Markov models. So how important are missing words? If like not all my important words are in the vocabulary, does this really matter? This paper here is, basically asking, are there embeddings showing up in the interior structures of the model that are similar to how the actual full word would be embedded? So is it like, basically, is it effectively learning something similar to the correct tokenization in embedding space? And, you know, by their measure, they're picking up about 70% retrieval. So another way of saying that is whether or not my words are in there is about 70% not important. On the other hand, maybe it's 30% important. So here's another study asking, like, well, what if we're using small models? And by small, these were on the order of 1 billion parameters. And what if we're doing a very specific application? And the application they were talking about was a programming language semantics study. And so they took this and did their task using all these three different algorithms that I actually mentioned earlier. And they also used for each one different sizes of vocabulary, and you can see, you know, in the performance measures, it does matter, right? It's like, you know, which one of these you pick in the size of the vocabulary is like has an impact on your performance. And I think that part of this may be having to do with the fact that these are smaller models, and they're measuring a very, very specific task. However, I think people are discovering that the compute cost and therefore the monetary cost of running very large models is driving people to look towards smaller models and application-specific tasks. And so if you take that point of view, it says, well, maybe, you know, maybe paying some attention to our tokenizer vocabularies does matter. And of course, people don't stop experimenting with things. This was an interesting paper where they tried a totally different architecture where instead of being given a list of tokens, it actually learns its own sort of ad hoc mapping of things into tokens on the fly. And so, you know, if one used this kind of architecture, we're not choosing a tokenization for it at all. So who can say what might happen with future LLM architectures? And so, having gone through that journey, we can ask ourselves: is you know, are tokens the master of our LLMs, or are LLMs the master of our tokens? And I think just like Lewis Carroll understood that there's no simple answer to that for people, I don't think there's a simple answer to this for LLMs either. It depends on like what's important to you, and maybe possibly things like, you know, application specificity or model size. So anyway, thank you for attending the talk. And as I said, all the code that you see is available on GitHub, so you can download these as Jupyter notebooks and play with this stuff yourself. Any questions?
Have you did the testing on different benchmarks to see if you varies the tokenization strategies and how the inferencing accuracy kind of changes? Have you tried it?
Yeah, so I mean, I haven't. Again, it's just not easy to do, but you know, this paper did, right? They had a task, and they did vary the tokenizers, and you know, that's exactly the test they were doing here. So again, I think it depends. Like, everybody has their own different application, and it's a difficult space to explore, because if we're just us trying to you know, figure out what this might mean for our application, the only way to really do the job right is to pick a different tokenization and then retrain an entire model and then run it on our application. I don't think many people are in a great position to do that. So I like to think that maybe if we all start experimenting with very smaller models like these billion parameters, it might actually be feasible. I mean, like, I can imagine running this job. I haven't tried it, but you You know, for something the size of, I don't know, Mistral or you know, one of these other larger popular models, I just don't think most people will be able to run these experiments.
Okay, I see. Yeah, thanks.
Any other questions?
There's over here.
It could be a silly one, but I'm just wondering, like, if we have already done tokenization on alphabets or on the words that we have around in English, then do we need to run tokenization again for different levels of applications? And if that is the case, why?
Can you repeat the last part?
So what I am trying to say is that if we already have done tokenization on English literature, then do we need to run the tokenization again for different level of applications? And if that is the case, why?
Oh, I think that like you kind of it doesn't work to re-tokenize just because, again, you can't change it without breaking the LLM. The LLM is all the weights are trained assuming a particular tokenization. So like if you tried to change it, it just simply wouldn't work. This is the problem. You could probably experiment with removing stuff. Like if you were trying to do an ablation study, you could take the vocabulary, you could take words and just mask them out and say, I'm going to pretend like it doesn't exist. You could then run and see what happens. I don't think you could add them. There's just no way to do that. So I don't. I guess if you're trying to do the experiment, you could like maybe try a bank shot where it's like, okay, if there's a bunch of words that like I care about studying, I could start with the vocabulary that has them, and then to do the comparison, I could just run like a slight hack on the model that masks them out and see what happens, and to put them back in. So that would be a way to do it.